So today I want to talk about the convolutional neural networks and deep learning and their applications in biometric. So we want to understand what are convolutional neural networks and how they can use to perform some object detections and other image classifications. First of all, deep learning are composition of nonlinear transformation of the data. It means that we try to find a method to directly extract features from the data. Till now, in the other machine learning based method, you select some feature descriptors and apply them on the data set, the train set in fact, and extract some features. Then you will give that features to the classifier and train a model according to that feature set. But we cannot say that any of the feature descriptors or feature extractors methods can be used in all of the problems. So finding the most appropriate feature descriptor is one of the problem. For example, in the face recognition, you try to use LBP feature descriptor, HOG feature descriptors, and also perform PCA and LDA dimensionality reduction methods to perform face recognition. But maybe in other type domains they cannot be works as good as face recognition one. So is it possible to find some automatic way to extract features from the training set without need to perform any type of hand engineered feature descriptor? The answer will be yes. By deep learning method, we can find a method to perform both of the feature extraction and classification tasks together in an end-to-end fashion, in fact, without need to do anything. You only need to construct an architecture for your CNN, then give it some samples. The CNN automatically extract the most appropriate and most discriminative feature sets from your data set, and then you can test the performance of your model and give it some unknown images and find the accuracy. So both of the feature extractions and classification tasks are performed in an automatic way. So the goal of deep learning is learn useful representations or features directly from data. Okay, first of all, the CNN is a method which uses supervised learning. As you know, in the supervised learning, we have some training samples, and for each samples we have a target label. So here, XI is the ith input training example, and this is the label, the truth label or the target label. Then we construct a model here. This black box is a model, and we can give it the unknown sample like X, and the model will predict the class label. And if this class label is the same as the real class label that we have for this test sample, we say that the model correctly classified this sample. Otherwise, we mention that it's incorrectly classified. By this way, we can compute the accuracy of the model. So this is the supervised learning, and CNN is also used as supervised learning method. So these are some of the applications of supervised learning: classification, denoising, and optical character recognition. In the classification, for example, we give it a an input image like a dog image here, and the model or this black box determine the class label which is most appropriate, most likely to this input image. And for this example, assume that the classifier predict the class label dog, which is correct for this example. For denoising, also we can create a model and give it some noisy image, and we expect to find the or noise removal image. And in this OCR or optical character recognition example, we give it an image consists of some handwritten digits or alphabets, and the system will give us a text or extract the text from this image and show it as the output. So for each of these black box in the traditional machine learning approach, you have to perform some type of operations like pre-processing, feature extractions, feature dimensionality reductions, and select a classifier like SVM, nearest neighborhood classifier, or any other ones, and then give that extracted feature vectors to the that classifier to train it and then test it. But in the supervised deep learning, we have different layers, and each layer has some learnable parameters, and each layer try to extract some type of the features from the previous layer. This is the first layer, so the first layer receives the input image and try to find some features from this one and then give it to the next layer, and the next layer receives the extracted features by the first layer and try to find some more complex feature from these input layers, these input features that receives from the previous layer, and it's give to the next layer, and in the last layer there is some softmax function, for example, and it give us the most probability of the target class, in this example dog. So deep learning is about learning feature representation in a compositional manner. Why learn features? So we have to learn some features in order to perform classification. So till now, by the traditional machine learning approaches, we have to perform all of these steps: pre-processing, feature extraction like HOG, SIFT, LBP, or other ones. Then we should perform some feature selection, for example, and finally we give it to the classifier like SVM. The whole method means called as a traditional machine learning approach, but this type of feature extraction, also known as hand engineered or handcrafted features. So you are responsible to select between all of the available feature descriptors, select one or some of them, and apply them in the target data set. The accuracy is completely related to the knowledge of the designer. If you select the best feature descriptors in that domain, the accuracy will be high, otherwise the accuracy can be low. So the most critical for accuracy, most time consuming in development, and we don't know which feature descriptor is better, and in fact what is the best features, and how we can, for example, perform some post-processing on this feature extracted, and which type of classifier we should select. So the deep learning method try to learn feature representation directly from data, so we don't need to perform any of this task anymore. So learn an end-to-end recognition system. Both of the feature extraction and classification tasks are performed by different layers in the CNN. So the CNN is a nonlinear mapping that takes raw pixels directly and convert them or map them to the labels. But how we can perform it, how we can build such a highly nonlinear systems, there are two approaches. By combining simple building blocks, we can create more and more complex systems. So these are two proposals. In the first one, we build a complicated function by using some simple function. This is exactly the way that genetic programming works. But in the second proposal, we use some simple nonlinear function and cascade the input of the output of one layer to the input of the next layer, and by this way, as we move from the early layer to the end, the function that we compute is become more and more complicated. So in the first method, as you can see, we have some simple functions, and for example, genetic programming try to find the most appropriate functions by combining these type of simple functions in order to find the mapping function, because we have some pixels in the image. These are the raw data, and you want to convert them to the label. How we can do it? Maybe we can find some functions by some combination of linear or non-linear functions. Maybe you can find a method that converts some pixels to a label. But here in the deep learning method, we give the raw pixels to this black box, and also we give it the class label. This is a car, and this black box consists of several simple nonlinear transformation blocks. We call each of them layer, and each layer is responsible to extract some simple features from their inputs. After they perform and extract these features, they give it to the next layer, and the next layer receives these input features and try to combine them and extract some more complicated features. So each black box can have trainable parameters, and their composition makes a highly nonlinear system. We call each of these small black box layers. So this is the input layer, and this is the output layer. So in each of the layers we have some trainable parameters, the weight and the bias for each of the neurons. So you know what is the weight and what is the neuron and activation function for the neurons. So in the CNN, again, in each of the layers we have some neurons, and each neuron is connected by some age to the other neurons, and we have some weight over each of these ages. Combination of the inputs of one neuron, for example, let me see here. Here we have a neuron, and this neuron is connected to some other neurons, and we receive some value here, and it will be multiplied by the weight. And here we have a summation of w1 times x1, w2 times x2, w3 times x3, w4 times x4, and after that we give it to the, after we find this multiplication and add it with some biases, then we give it to the nonlinear function, for example rectified linear unit, which is the most popular one in the CNN, and this function only find this formula, the maximum between the input and 0. So if the input is negative, we assume it as 0. Otherwise, if it is more than 0, this function return the input argument. So this is the way that each of the neurons works. The nonlinear function in this example is a I think tangent hyperbolic function. Anyway, so in the normal neural network architecture, we have different layers, and each layer has its own trainable weights. We give it some input sample, and also we have one label or truth label for that input sample. So in the forward propagation, the input sample will be multiplied by the weights that we have here, and finally as the output of the neural network we have one predicted value, for example y hat. So for this sample we have the predicted result, and also we know the truth label or truth value for this sample. Then we can compute the error, and the error will be back propagated and updated all of the weights, so that next time that this sample offered to the neural network, the predicted value or the y hat should be better than the previous time. So we have multi-layer neural network with more than 2 layers, are nowadays called deep nets. It's not a real definition for deep nets. This is multi-layer perceptron definition, in fact. So as the engineer, you are responsible to specify the number of layers and number of neurons in each layer, and also the loss function for the last layer. So as I said, in the forward propagation, we offer each of the samples to the network, and when we move forward, it will be multiplied by the layers weights, and then we compute the output and compare it with the truth output of that label, that input sample, compute the error, and we update the weights by performing back propagation and gradient descent algorithm. So this is the formula for updating the weight. This is the loss function, and this is the learning rate, and the weight will be updated by this formula. So next time that we offer the same sample, the error will be reduced. But the neural network cannot be used successfully in image recognition, because in neural network each of the neurons should be connected to all of the pixels. For example, here see, if we have, for example, an image with 1000 by 1000 pixels, and assume that we have 1 million hidden units, then we have 1 billion parameters, which is not possible to train them by even a supercomputer. because each of these pixels should be connected to 1000 by 1000 pixels, and we have here 1000 by 1000 weights, and all of them should be trained, all of them should be adjusted, and we should learn which value is most appropriate for them by offering some samples. But in fact, in an image we have some specific properties. A spatial correlation is local. The pixels around each other has some meaning. This is the eyes. So the value of these pixels are related to its neighbors, but it's not related to this part. And also, in order to recognize an image, we don't need to recognize every pixel. We want to find some specific features. Here, in the CNN, each of the neuron is only connected to a specific area of the image. So they only check the relation between that pixels and its locally neighbors. We don't need to connect each neuron to all of the pixels in the image. For example, if we have a filter by 3 by 3, then each of the neurons has only connected to the 9 pixels. In this example, but again we have a 1000 by 1000 image, and assume that the filter size is 10 by 10, so we consider only 100 pixels. So now we have 10 million parameters. Even by this way, there are this 10 million parameters is huge. So let's see how we can reduce the necessary connection. Reuse the same kernel everywhere. So since we are interested to find some type of the features in the image, and we don't know where is that specific features in the image, we can check the same weights or same filters for everywhere. So this neuron is connected to this part of the image, and the weight of these neurons is completely the same as the next one. So all of these neurons try to find the same features in the different locations, in the different patches of the image. So share the same parameters across different locations, and this is the way that convolutional neural networks works. And the type of operation in each of these small patches are performing some convolutions. So instead of multiplying the weights by this one, we perform some convolutions. As you remember from the image processing, we can convolve a filter over an image in order to extract some specific type of the features. So this is the convolution operation. We have a specific filter, and this filter will be applied in this part of the image, and finally we find one value, and this value will be this is the extracted feature. Then we should perform the same operation on the next part, and we slide this filter over the image till we reach the end. For example, here, as you can see, this filter is applied and we find this extracted feature. We call the extracted feature as feature map. This is the feature map of the first filter, and this is the other feature that extracted by another filter. So now each of the neuron can perform one of these convolution the first neuron perform this part and find the result of this pixel. The next neuron perform the next convolution. So in fact, each of the neuron convolve the filter, the same filter, to different places of the image. This is the reason that we call it convolutional neural network. So by one feature you cannot do many things, so we can extract different type of the features. As you saw in the previous animation, we perform, for example, two type of the filters and extract two type of the feature map. Here we have multiple filters and we apply them to the image. But what type of the filter? Edge detection, corner detection filters, or which type? In fact, we don't know which type of the filter you need. The value of the filters will be learned by backpropagation and gradient descent algorithm. In fact, we initialize all of the weights by random value, and the CNN automatically learn which type of the filter are useful for this layer. Here we have one specific filters which determine vertical lines in an image. Okay, so this is one of the famous filters, but we never use this type of predefined filters. This value will be trained by the CNN automatically. So,
Professor, I have a question.
Yes.
How I get the -3 output? Can you please tell me the calculation of this?
There are some negative weights here, -1, -2, -1. So if you multiply them by this pixels value, 3 times -1, okay, 0 times 0, nothing, 1 by 1 is okay, 2 by 2 is 2 by -2, -4, 6 by 0, nothing, 2 by 2, okay, 2 by -1, 4 by 0, 1 by 1. So what's the problem? This is -3, this is 1, this is -2, -4, -7, again -3, -5, -5 plus 1, -4 is correct. Maybe there is some problem with these numbers. I didn't compute them by myself. It seems that the answer is -4. But since we have some negative values in the filters here, this is a Sobel filter, so it is possible to receive some negative feature value here, and we call all of this page or this n by n matrix as the feature map. But here we don't know what value will be used as the kernel value. So the CNN should learn them from the input image that we offer to the system. So we use multiple filters. Now by this, if we have 100 filters and each filter's size is 10 by 10, we have only 10,000 parameters in this example. But the first one we have 1 billion, and the next one we have 10 millions. But now we have, by this way, we have 10k or 10,000 parameters, because we use the same weight for all of them. The same kernel will be used for each of these neurons. So if we have 9 or we have, for example, 10 by 10 kernel, which is very high, we never use this size of the filters. The filters are normally 3 by 3, 5 by 5, 7 by 7, and most of the times we use 3 by 3 only. So we have only 9 weights. for each of the neurons here. So if I have 1000 neurons here, only we have 9 weight for these filters. All of these 1000 neurons have the same weight, and the weights are shared between them. So in most of the case, the input image are colorful. We have 3 channels, red, green, blue. So when we want to apply a filter, we use the same filter for each of these channels. So in fact, the filter is a 3-dimensional filter, 3 by 3 by 3, for example, or 7 by 7 is the size of the filter, and there is a depth of 3. So we have a block. In fact, the size is m by n by 3 for this layer. For the next layer, it can be more than 3. So output of convolving one feature is called a feature map. So when you convolve this feature, filter to whole of this image, there will be one output, and this output is called as a feature map. This is just a sliding window. The output of the one part filter of DPM is a feature map. So here, this is the feature map of the first filter. Then we have another filter in the same layer. This is the input layer. This is the first layer. In the first layer, we try to learn multiple features. This is one of the features that we learn, but it is not enough. So we learn multiple features. For example, 10, 20, 30 different features will be learned from the input layer. Each filter detects features in the output of previous layer. So to capture different features, learn multiple filters. Here, as you can see, we use different color of here, and each of this rectangle with different shape color means that we use different filters, and all of them are applied to in all of the channels. For example, RGB, we apply the same thing in the RGB, and if it is more than 3, we apply the same filter in the next ones. So these filters can be considered as a block. So here, this neuron has several. For each of the neurons here, we have 5 different filters. So after I apply these filters to this image, we will receive 5 different feature map. So we will show it by a cube shape or 3-dimensional shape. It means that we have 5 different feature map extracted by 5 different filters. And here, as you can see, the filters, the same filter applied to all of the input channels. In this example, 3. But for the next one, each of the filter will be applied to 5 different channels. The same rectangular filter will be applied to the first, second, third, fourth, and fifth feature map that we extracted here, because we give these features to the next layer, and the next layer is the same as this one. It has different number of neurons, different type of the filters, and try to extract some complicated features from these features that we extracted from input image. Let's see what they mention here. Each neuron in the convolutional layer is connected only to a local region in the input volume, especially, but to the full depth. So this one is only connected to this part, but also second layer, third layer, and any other layers that we have here. So we have, for example, 100 by 100 neurons here. each of the neurons only connected to a small area of the input image or previous layer. So this is a famous image of the convolutional neural networks. As you can see, we have one input image. Assume that it has 3 channels RGB. This small neuron only connected to some part of this image, and as you can see, this filter is applied to all of the channels. And here we have different extracted features. For example, 10, 20 features are extracted here. For the next layer, for now, ignore this one. This filter applied to these features, but as you can see, not only from it's applied to this part of the features, to all of the channels. For example, 10, 20, the depth of this layer, if it is 10, this filter applied to all of these 10 channels. And by this part we perform feature learning, and then we will perform the classification by some fully connected and softmax. I will explain it. So these are 2 feature maps that are extracted from this input image. So one of the properties of convolutional operation is translation equivariance. Means that we can find the same features in, for example, we are looking for the eye in one image, so we don't know where is the eye, so we can perform the convolution of one filter to assume that we have a filter to compute which give us 1 whenever there is an eye in the image, otherwise it give us negative or a small number. So if you want to find it, you should apply that filter to every small region of the input image. In order to reduce the size of the extracted features, we can perform some subsampling. We call it pooling. So by pooling, we can filter responses at different locations in order to gain the robustness of the extracted features to the difference in locations. So as you can see, here we know that there is a one eye in this part. So one of these neurons output is the highest one. We only consider that part. So instead of this 9 location, I only consider the maximum one. And now this neuron show me there is one eye in the image in a very larger area of the image. Then I can give it to the next layer and extract some other type of the features from this eye. Maybe combine it with the eyebrow and nose and some other facial part in order to recognize the person. But here we know that we find one eye and we don't need all of these features. One of them is enough, the one with the highest value or the average of them. Anyway, we can reduce the size of the extracted features by using pooling. So pooling also subsamples the image, allowing the next layer to look at larger spatial regions. So every typical convolutional neural network consists of these layers, some convolutional layers, then we perform some non-linearity function like ReLU layer, rectified linear unit, and then we perform some subsampling to reduce the size, and perform some normalization. By this way we compute one feature map, and these feature maps will be given as the input of the next layer. So the CNN is a stack of some combination of these layers. The convolutional layer is essential, but and also the non-linearity is essential, but the spatial pooling and normalization are optional, but most of them are used in famous architectures. So stack them up and train just like multi-layer neural network. The final layer is usually fully connected neural network with the same number of neurons as the number of classes that you have. For example, if you want to create a neural network for the AT&T dataset that we use for LBP, PCA, and other feature descriptors, the last layer of your CNN should give us the probability of the input or test samples belongs to each class. So we need 40 different neurons, and then by using a softmax function we select the class with the most or highest probability. Revisiting the composition idea, every layer learns a feature detector by combining the output of the layer before. So the early layer will learn some simple features, then they give it to the next layer, and the next layer combine these features to extract more and more complicated features. Let me first find something about this part. Okay, here. So this is the feature visualization of the first layer of one CNN, which is trained on a very large data set. As you can see, each of this one are a filter, and the size of these filters are 11 by 11 by 3, and as you can see, some of them are similar to the vertical line, diagonal line, horizontal line, some blobs, some edge detector. So these are very similar to the famous filters that we learn in the image processing. For example, this filter apply on the image and it give you 1 whenever there is a blob, there is a pink blob in the image, in that part. Or this one can reduce 1 whenever we apply it to some part of the image and most of the pixels are blue. It will be used, for example, for detecting the sky or sea or water. The next layer combine these simple features, and as you can see, if you visualize the features in the next layer, they can find more complicated features in the image. For example, some part of the face, is there any some part of this face in the image, or here some small textures, or here are there any region consist of this part. In fact, I think this is not really the visualization of the second layer. You cannot expect the second layer to find these complicated features. For example, 2 edge can be combined and give you 1 corner, but or 2 line can be combined and give you a rectangle or triangle, but you cannot expect the second layer to learn this type of the features. Note how the previous low-level features are combined to detect a little more abstract feature like texture. Okay, this is not little more abstract feature, it's complicated features. These are similar to the last layer, I think. But for this presentation, they use this slide. So as you can see, this is the third layer, and now we have more and more complicated features. And this is the fourth layer, and now we have the whole animal, for example, or whole objects. Okay, so this is one of the earliest famous architecture. We call it AlexNet. It's this is the winner of ILS-VRC challenge in 2012. There is a specific data set which is consists of 1.2 million images, and there are 150,000 test images, and the images are from 1000 categories. As you can see in this image, we have different type of the categories, objects, for example, dish, home, computer, animal, piano, different type of animals, flute, persons, watch, dogs. We have 1000 different categories in this competition, and this competition is also continued after 2012, and most of the famous architecture that are known best known today are proposed during this competition, like GoogleNet, ResNet, InceptionNet. All of them are the winner of this competition in different years. So this is the first year that the competition were held, and the AlexNet, which is provided by this guy, Alex Krizhevsky et al., is the winner. This is the error of this network, 80.2% in top 5. Again, what is the meaning of top 5 error? It means that the system predicts 5 labels, and if the answer or correct label is between one of these 5, we accept it. It doesn't need to be the only the system doesn't only predict one label. We give it a chance to predict 5 labels. The 5 best most likely labels will be predicted by the system, and then we check it. If the truth label of the object is between one of these 5, we accept it and we say that this image is classified correctly. Only 18% of the samples are not correctly recognized, but in the for example 2016 or 15, this value become 3 or 4% error, and if a human even try to participate on this challenge and use his vision system and his brain in order to decide about this test samples, the human is also answers are more than 5% error. So the last winner of this competition outperforms human visual system. But this is the earliest one, and the accuracy was 80.2. This is the architecture of AlexNet. We have one input image, then we perform in the layer one convolutional and one pooling, Then second convolutional, again we have, as you can see, 5 different convolutional layers, and some of them consist of pooling, some of them only perform convolutional and rectified linear unit. They didn't mention about ReLU. The ReLU is the essential layer, so it is inside the convolutional. So as we said, the pooling is optional. This is the shape that presented by the Alex in his paper. As you can see, this is the input image, 224 by 224 by 3, the input image of this ImageNet dataset. This is the filter size, 5 by 5, and in the first layer they extract 48 different features. So we have 48 feature map, or we train 48 different filters in the first layer. Then we give it to the max pooling, and max pooling reduce the size by 2. So as you can see, the size of the next one, what's that, 55, 48, 128. Each time that we use a max pooling with kernel size 2 by 2, the size of the image will be subsampled by factor 2. So if the input image is, for example, 256 by 256, after one max pooling it will be 128 by 128. But I don't know, this is the number of filters, this is the kernel size, what is this 55, and now why it is become 27 here, 27 to 30. As you can see, this is the half of this one. This is 55. Okay, this is 55 divided by 2 is 27, 27 divided by 2 is 13, 13 divided by 2, no, we don't need, as you can see here, we don't have any pooling. So this is the last one, this pooling, and then we give it to the dense function, dense layer. Dense layer is a simple multi-layer perceptron neural network. And finally, the output layer, as I told you, should consist of the same number of neurons that we have in the classes. So we have 1000 classes, so we have one layer in the here with exact 1000 neurons. So when I give it one image, one of these output will be maximum. We consider that one as the predicted label. There is 1000 neurons here. When you give the one input image to this neural network or this CNN, each of these pixel will be multiplied by this weight and move forward. So in the forward propagation, we receive as the output 1000 numbers. So softmax say that find the maximum between them and use that neuron label as the output label of these samples. So for example, the first neuron is dog, the next one is tiger, the next one is lion, the next one is, for example, keyboard, mouse. So we find out which of them give us the largest probability. Then we assign that neuron label to this test sample. Let me see. So CNN can be considered as generic feature descriptors or generic feature extractors. This is the convolutional layer, and then we give it to the pooling, and the pooling, as you can see, the size of this image, the extracted feature map will be reduced by 2. Then we extract some other features here again by convolutional and ReLU, and then we give it to the next pooling, and by this way when we move forward the size of the this extracted feature map will be reduced. Finally, we should give it to the classification part of the CNN. In the classification, the last extracted feature map will be flattened. We convert it to the linear version, and then there is a fully connected or multi-layer perceptron here, and finally we have the output layer, and the activation function for these neurons are softmax. So this image will be given to the system, and then the car, truck, van, and other type of the neurons that we have, each, or bicycle, each one give us one value. By softmax we select the most value or the biggest value and consider this image as belong to that category. This is an animation which show you how the convolutional works. Here we can see the max pooling. So this is the extracted features, for example, in this layer. Then by applying a max pooling by filter size 2 by 2, we select between each of these 4 numbers the most or the maximum one. Between these 4 number, 6, this part we select 8, this part we select 3, and from this blue part we select 4. So by applying this max pooling, these extracted features, which is 224 by 224 by 64, now convert to 112, 112, 64. So only we didn't change the depth. The depth is the number of features, but the size of the feature map should be reduced. 64 features now with the size of 112 by 112. Here you can see the visualization of the learned features in different layers. When we move to the last layer, the extracted feature will be more and more abstract. So now this neural network, this CNN output layer consists of 5 neurons, and this input has the most probably is a car, for example 80%, 10% truck, 6%, the summation should be 1. So for example 75% here, 10% here, 5% here, 6% here. So this is not horse, this is not sheep, this is not airplane, this is a car. So the early layer extracts some low level features. The mid level features, as you can see in this figure, we can see better than the previous one. The early layer only extracts some blobs and some edge detectors. Now they combine them, and now we can see some, for example, circular like wheel. And here we can see more and more complicated features. This is the real visualization of the learned feature of the CNN.